in this section of the book, the prelude to the definite integral, we actually start looking at kind of the fundamental notion that we want to look for in integral calculus. In a sense, it's analogous to what we did in differential calculus. In differential calculus, you have a notion of the average rate of change, the change in one quantity divided by the change in the other. But you believe that there was something called, for instance, the instantaneous velocity. So you know how to define the average velocity. You believe that there's an instantaneous velocity, the velocity at some time. And we took the limit of the average velocities, the average rate of change of position with respect to time, and used that to define the instantaneous velocity. The definite integral, you should think of it as a continuous sum of infinitesimal contributions. But like instantaneous velocity, we don't even really have a definition of that. We don't know what it means, but we're going to have some finite things, kind of the analog of average rates of change. We're going to have some quantities that we can calculate called Riemann sums, and then we're going to see that, yes, if you take limits of Riemann sums, you should get these other quantities that we physically, intuitively know exist. And we'll take limits of Riemann sums and use those to define the definite integral. Okay, so let's look at an example of what it is that we're trying to approximate and calculate. So here's an example. We'll return to velocity again. So an example. Suppose you've got a car traveling along a straight road. Between times, we're going to look at a fairly small interval of time. Between times, t equals 0 seconds, and t equals 2 seconds. So traveling along a straight road, that's so that we can talk about the position. We think of it as a coordinate axis, and we can talk about the position. We assume we picked a positive direction, negative direction, marked off the road with, we're going to use meters here. The times between 0 and 2 seconds, this just means that we started our stopwatches, or we just declared, here's the point in time that we care about. We call that t equals 0, and here's 2 seconds later. Okay, and then what we want to look at is, suppose you're given some velocities at different times between 0 and 2 seconds. Can you estimate how far the car has traveled in that time, or more accurately, the car's displacement during that time? So here's our fundamental question. Given the velocity, so I mean the instantaneous velocity, which you read off the speedometer, if you also include that you note which direction you're moving in, the positive or negative direction. Given the velocity of the car, at various times, how do we estimate, or how can we estimate the change in position so I'll call the position P of t. I'll measure that in meters. Measure the change in position P of t in meters between t equals 0 and t equals 2 seconds. So this is our fundamental question that we want to start with. It's, it's a natural question. You've got the velocities. How would you estimate how far you've gone? Well, so this quantity, the change in position, so the change in position P of 2 minus P of 0, this is called the displacement. It is not necessarily the total distance traveled. It's you've marked off positions along this road, and it's the position at 2 minus the position at 0. So if the car changes direction, this change in position would not be the same as the total distance traveled. For instance, if the car in 2 seconds went forward in the first second and backed up to where it started in the second second, it would end up back where it started. The displacement would be 0, but the total distance traveled wouldn't be. All right, so this is the displacement. How do we estimate this displacement given some velocities? So I want to just pick some velocities, and then I want to talk about how you would estimate it. So I want my numbers to match the numbers that are in the book. So let me look. So suppose we know the following. So between times 0 and 0.3 seconds. So okay. The velocity of the car is 30 meters per second. I'm going to pick some other ones, but let me comment on this for a minute. 2 seconds. Can a car change its speed appreciably, or its velocity appreciably in 2 seconds? Yes. If you step on, well, depends on the car, but if you step on the accelerator, push it to the floor or slam on the brakes, you can change the velocity of a car a noticeable amount in 2 seconds. Can you change the velocity of a car very much in 0.3 seconds? Well, it's not as much. And it's a question of what you think is a significant change in the velocity, really. But it's hard to imagine doing too much that would change it a substantial amount in 0.3 seconds. Maybe, though, you want to go down to 0.1 seconds. But we don't want to have to do too huge a sum in our estimate. So I'm just going to pick some time intervals that are smaller than 2, some subintervals of the interval from 0 to 2. And it's our hope that those are small enough subintervals that the velocity doesn't change too much on those intervals. Of course, what too much means is part of the problem in defining the definite integral. All right, so I'm assuming that at some time t1 between 0 and 0.3 seconds. And let me say something about between. In English, between is unclear when you say something's between 2 times. Do you allow your time to equal the times you're saying it's between? So I said t1 is between 0 and 0.3 seconds, and I'm allowing it to be equal. Just so that we can be clear, when I say between, I'm going to mean I allow that it equals the endpoints. If I want to disallow that you can include the endpoints, so disallow equality with the endpoints, I'll say strictly between, and that's supposed to mean you'd have strict inequalities here and here. All right, so suppose we know at sometime t1 between 0 and 0.3 seconds, the velocity is 30 meters per second. At some time t2, so at some time t2, where t2 is between 0.3 seconds and 0.8 seconds, the velocity is 20 meters per second at some time t3. Between 0.8 seconds and 1.2 seconds, the velocity is 10 meters per second. And finally, at least for now, at some time t4, between 1.2 and 2 seconds, the velocity is minus 2 meters per second. So the car has reverse direction and is headed in the negative direction at a speed of 2 meters per second. Given this data, how would we estimate the change in position, so the displacement of the car between times 0 and 2 seconds? Well, you do what you would probably do naturally, but we should go through it carefully at least a few times. So what do? Well, you take a look at P of 2 minus P of 0, and you write a telescoping sum for it. We talked about telescoping sums in the last section. This is a particularly simple case. I guess it's no more simple or no harder or easier than any other telescoping sum. You write this as P of 2 minus P of 1.2 plus P at 1.2 minus P at 0.8 plus P at 0.8 minus P at 0.3, and then plus P at 0.3 minus P of 0. All right, why do this? Well, first of all, the equality is true because this telescopes. Here's minus this plus this, so these cancel. There's minus this plus this, these cancel. Minus this plus this, these cancel. You're left with the P of 2 minus P of 0. Yes, the sum telescopes. All the in-between terms collapse. But why did I break it up like this? Because between 1.2 and 2 is when we were given a velocity. We were given t4 in that interval. And in this interval, between 0.8 and 1.2, we were given the velocity at time t3. Between here and here, we were given the velocity at time t2, and between here and here, we were given the velocity at time t1. We don't know what t1, t2, t3, and t4 are, but we're told the velocities at those times. So what do? Well, velocity, the instantaneous velocity, is the limit as delta t approaches 0 of the change in position over the change in time. Now, these changes in time aren't ridiculously small, but they're small. And so what we hope is that the instantaneous velocity is approximately equal to, of course, again, it depends on what you mean by approximately, is approximately equal to the change in position over the change in time if delta t is small. So that means if delta t is close to 0. All right, but we're given some instantaneous velocities. And so what does this do for us? So if you call the instantaneous velocity v, so this would be a v, and you multiply both sides by delta p, what we're using, or what we're going to use, is that the change in position should approximately be the velocity times the change in time. You might think, what do you mean approximately? I learned a long time ago in high school that the change in position is the velocity times the change in time. Well, they were talking about average velocity or constant velocity. If your velocity is constant, then it's the same as the average. This is the instantaneous velocity at a particular time, and then you multiply times delta t. That only gives you an approximation to your change in displacement if your velocity is not constant. But this is the approximation that we're going to use, so that, and we use as small a time interval as we've got, as we can, and that's why we split the sum up this way, because now we're going to say that each of these sum ends, these smaller sum ends, are approximately equal to the velocity at a given time times the change in time. At what time? The only times that are given to us, although the times aren't, but we gave them names, T1, T2, T3, and T4, where we're given the velocities. We're going to say that, oh, P of 2 minus P of 1.2 is approximately the instantaneous velocity at time T4 times the change in time, which is 2 minus 1.2. Right? So this is the velocity at time T4 times the change in time on this subinterval. It should be approximately this displacement. It could be exact, but we don't know that unless we were told something like the velocity is constant in that time interval. Plus, on this subinterval, the one from 0.8 to 1.2, we're going to use that we're given the velocity at time t3, which is between 0.8 and 1.2. And we're told that that's, well, I'll put in the numbers in a minute. And then we'll multiply times the change in time there. And we'll add the velocity at time t2 times the change in time on this subinterval. And then finally we'll add the velocity at time t1 times the change in time here. Okay, so this is going to be our approximation for the displacement. I need this space. So if you plug in the numbers, I'm writing equals because of what I'm writing equals this line, but it's all approximately equal to the displacement. We were given that the velocity at time t4 is minus 2. So you get minus 2 times 0.8 plus the velocity at time t3 we were given was 10. I'm dropping the units, but it's meters per second and seconds, so we're going to end up with meters. 10 times 0.4 plus the velocity at time t2, which is 20 times 0.5, and the velocity at time t1, which is 30 times 0.3. And you add all these up, so we get a minus 1.6, a plus 4, a plus 10, and plus 9. So I get 23 minus 1.6, so a 21.4 meters. So this is our approximation for the total displacement. For the displacement of the car, so its change in position between times 0 and 2 seconds. All right. How could we make this better? Well, maybe you think these intervals of time are too big. So we should take smaller intervals of time. Of course, then we'd need to be given more velocities. velocities in each of our new subintervals. So I do want to look at that. I want to just divide this biggest subinterval, this one that has length. So the time interval is 0.8 seconds in here, which seems a little big compared to the others. But first, let me put this in table form where it will look a little nicer. All this data is too spread out. So yeah, in a table form, this data looks a little better. I want 4 rows and 5 columns. So, well, it looks a lot better in the book. My my ability to draw very rectangular tables on the board is, yeah, we'll see. Okay, so what do we want to put in? The subinterval. The subinterval of time that we care about in seconds. I'm not going to write everything on the board. So the subintervals that we care about. So what am I talking about? Subintervals of the time interval from 0 to 2. We looked at the time interval from 0 to 0.3. So that's 0 to 0.3. And the time interval from 0.3 to 0.8. And the time interval from 0.8 to 1.2. And then and then 1.2 to 2. So those were our time intervals. So subintervals of our original interval from 0 to 2. And then we had different times, one for each of these subintervals, at which we knew the velocity. We were told the velocity. So we don't actually have numbers, but I'll go ahead and write T1, T2, T3, and T4. These are the times, the names for the times that these are in these subintervals, the times at which we're given the velocities. And what are the velocities that we're given? In meters per second, but I won't write the units. We were given 30, 20, 10, and minus 2. And then there's the line you calculate, the approximate change in position on each of the subintervals, and then you're going to add these together. So it's this number times the length of that subinterval. Right, so this is where we got 9. Right, and then it's this number times the length of that subinterval, 10. And this number times the length of that subinterval, which is when we got 4. And this number times the length of that subinterval, negative 1.6. Right? Those numbers that I wrote, these are the approximate changes in position on each of the subintervals, and then the total approximation for the change in position. So the total approximate, or the approximate total, maybe I should say that, the approximate total change in position. So the approximate P of 2 minus P of 0 is the sum of these. So I'm writing equals because I've written the approximate. But then you add these numbers like we did a minute ago, and you get the 21.4 meters. All right, so it looks nice in a table. What would we like to do? Well, ideally you would have smaller subintervals, so really could the velocity change much in 0.1 second? It's hard to believe. So maybe if we had more subintervals, each one with only 0.1 seconds, we'd be really happy with our approximation. But let's just do an example where instead we chop up this last subinterval into two pieces of equal length. So this one has length 0.8. Half of that would be 0.4. So we want to go up 0.4 from 1.2. So that would be 1.6. And then maybe we're given some data about what happens on the time interval. So on this time interval and this time interval. Okay. So what do we need to do now? We would need times here in each of these subintervals, velocities here at those corresponding times, and then we'll calculate the changes in displacement, or the approximate displacement, changes in position. T4 was somewhere between 1.2 and 2. So it's in one of these subintervals. Without more data, we don't know where T sub 4 is. Or if one piece of data would be, what is T4? Or if T4 is 1.6, it's in both of these subintervals because they're closed, and we could put it either place and pick one and need data in the other subinterval. Just in this example, I'm going to assume that now we know T4 is in this subinterval, but that's an assumption. It's not something that follows from anything we were given earlier. And so I'm going to assume T4 was in this subinterval, and that now somebody gives us that at some time between 1.6 and 2, that we know the velocity, if I want to match the book, is -5 meters per second. All right. So what approximate displacements do we get on each of these subintervals? Well, you take this and you multiply by the length of this subinterval. The length of that subinterval is 0.4 times -2, so we get a -0.8. And then the length of this subinterval is 0.4 times this, so we get a -2. Okay, so this was our first approximation. Our second approximation that we get, assuming that we have the data that's now in this table, is, well, the first three numbers didn't change. So that still adds up to 23. But now we subtract, well, you add in this, or you subtract this 0.8, and you subtract 2. So we went from 23 minus 2, so that's 21. So 20.2 meters. Okay. That's what we get now. The question is, or one of the questions is this a better approximation than that? We were given more data. Our time intervals are smaller. We know that the velocity went way down, or the speed went up, but in the negative direction from here. So you might be tempted to say this is a better approximation than that. In fact, we can't really know that. It's kind of unknowable because what could happen is that before we assumed our approximation basically assumed that the velocity was -2 on the whole interval from 1.2 to 2. Now we're assuming that on half of this interval the velocity was -2, but on the other half it's -5 meters per second. Well, does this give us something better or worse? It's conceivable that in fact on the subinterval from 1.2 to 2, the velocity is always very close to -2, except ridiculously close to T5 the velocity is -5, but almost every place else it's closer to -2. Well, if that were the case, then this approximation could easily be better than this one, and you would expect it to be. Now, it's kind of hard to believe because we were down to 0.4 seconds. -5 is significantly different from -2. Could -2 really have yielded a better approximation on that whole interval? It just depends. And we don't want to worry too much about the physical characteristics of a car, because if it were a particle and its speed was something completely different, or its physical properties are completely different, we might have no intuition for what it could do in 0.4 seconds. However, we do have this feeling that if you take smaller intervals of time and do this approximation, that things get better. And part of the problem, or part of the interesting part of defining the definite integral, is defining what it means that things get better when you take smaller intervals. This is really a topic for the next section when we define the definite integral and talk about when it exists, but I do want to go ahead and say, I want to give you some feel for what we're going to do, and I want you to understand what we can say about if you make the intervals smaller, the approximation gets better. So, first, I want to assume, so this is a remark on, this is a remark about, does the approximation, or in what way, how about in what way does the approximation get better if you take smaller intervals? Okay. First, I want to assume that the velocity is a continuous function of time. If the velocity is not continuous, well, first of all, physically it should be, but if it weren't and could just kind of arbitrarily jump all over the place, then yeah, there's no hope of knowing that as you take smaller time intervals and just take arbitrary times in those time intervals, that anything reasonable happens. So first assume v of t equals the velocity of the car is continuous. So as the time changes a little bit, the velocity can only change a little bit. Then what? What I want to say is, under the assumption that the velocity is a continuous function, that if you take your time subintervals small enough, you can make your displacement approximation as close to the actual displacement as you want. So you have to kind of give a name to the as you want part. How close do you want the our approximation to be to the displacement? So let epsilon be greater than 0. What you should think is that epsilon is a measure, is small. It could be anything greater than 0, but what we care about is when it's small, it's supposed to be the measure of how close your approximation of the displacement is to the actual displacement. So you pick that. You tell somebody, I want to know that my approximation of the displacement by the process we were using is within 0.00001 of the actual displacement. Let epsilon be greater than 0. Then you can take subintervals of small enough length so that for every choice, so that our approximation of the displacement, so I'm still using the same example of P of 2 minus P of 0, is within epsilon of the actual value of P of 2 minus P of 0. All right. What do I mean? I mean, so you can if someone tells you how close they want your approximation of the displacement to be to the actual value of the approximation of the displacement, it is possible to take small enough subintervals. What does that mean? It really technically means there exists a delta greater than 0 such that if all of your subintervals have length less than delta, and if you are given the velocity at one time in each of your subintervals, and you go through this process that we did of taking the velocity at that given time, multiplying by the length of the subinterval, and adding, if you go through that process to estimate the displacement, and you've picked your subinterval of length smaller than this delta greater than 0, then you can make that approximation be within epsilon of P of 2 minus P of 0. This is a big theorem that you can do that. It's the existence of the definite integral and at least partially, well, depending on how you look at the problem, partially the fundamental theorem of calculus as well, that this can be done. But that's the best statement you can make, and it's hard to know what this delta greater than 0 is, so what small enough means, unless you're actually given a formula for the velocity, and even then, it's a difficult problem. But this can be proved, and so it tells us if the time intervals are small enough, you can get arbitrarily close to the displacement. But what it doesn't tell you is that once you're small enough that if you take something smaller, it actually gives you a better approximation. It's a little delicate, but this is something we can say. It is not that if you're given a set of data and you subdivide those intervals and you're given another set of data, it is never the case that you can know. Well, it's not never, because if you were actually given the velocity as a function of time so that you could know, but if you're just given the velocities at specific times, you will never know that your approximation using smaller subintervals is necessarily better than your approximation using bigger subintervals. Still, it's what you expect to be true. You suspect that if you take smaller subintervals, you get better approximations, and we'll do that kind of thing fairly often. All right, I want to give some names to various things that we've done. Chopping the subintervals up, we need some notation and terminology for it. Picking times in each subinterval at which we're given the velocities. We need a name for those points. This process of calculating this number times the length of that subinterval and then adding them together, we need notation and terminology for that. So that is what I want to do now. All right. I'd like to leave that on the board, but we'll see. So we have to define a bunch of things now. It's kind of unavoidable. It'll help us later. So definition. So suppose we have two numbers, A and B. A is less than B. We're going to look at the subinterval from A to, or the interval from A to B, and we want to talk about chopping it up into subintervals. So a partition of the interval from A to B. We'd like for it to be the subintervals that we chop A, B up into, but it's easiest just to say that the partition is a set of endpoints of the subintervals, because that's an easier piece of data to talk about. Partition of AB, partition, let's see, I guess I'll use a script P for this. A partition P of AB is an ordered set, but I'll just use set notation. It's an ordered set x0, x1 through xn. So some finite collection of values such that we want this to be this set to be giving us the endpoints of the subintervals that we chop this up into. That means that x0 needs to be A, such that x0 equals A. We need xn to be B. And everything else is in order and they're in between. So you need x0 less than x1, less than x2, and so on. That's a partition of AB, but you should think of it as giving you all the subintervals. So, in fact, the ith subinterval of the partition P is really just this set, but when you talk about the ith subinterval of the partition, you mean the subinterval, so like the first subinterval goes from x0 to x1. The ith subinterval it would go from x sub I minus 1 to x sub I. So this is the ith subinterval of P. So I'll say it again, when I is 1, so the first, the 1th, the first subinterval of P goes from x0 to x1. The second subinterval, that's when I is 2, goes from x sub 2 minus 1 to x sub 2. So from x1 to x2. The nth subinterval goes from x sub n minus 1 to x sub n. In keeping with our notation from the last section for finite differences, x sub I is a function of an integer, and so we can look at the finite difference delta x sub I, which, if you recall from last section, means you would take x sub I minus x sub I minus 1. This is the length of the ith subinterval. Okay, I need to define the mesh of the partition, the set of sample points, and a sample partition. Maybe I'll the mesh, I'm trying to save this data, the mesh M sub p of the partition is the length of the longest subinterval of the partition. Of course, there might be more than one interval that has the same longest length, but we're interested in the length of it, so we just take the biggest length that occurs. Is the length of one of the longest subintervals of the partition. So I'll just say subintervals of P. Okay. The point of this is that saying that the mesh is small, so saying it's less than some delta, implies every subinterval is less than delta, has length less than delta, because you've said the biggest one has length less than delta, so they all must. That's the mesh. We want a set of things that play the role of these times at which we were given data. That's called a set of sample points. A set S, that's a script, supposed to be a script S. How many sample points? We need one in each subinterval. There are n subintervals here. Right? N subintervals. Our partition has n plus 1 elements in it, but the number of subintervals is just n. So we want one of these. We're going to call these sample points, one sample point per interval. So we need an S1 through Sn. A set of sample points for P. Provided all we want that the ith one is in the ith subinterval, provided that x sub I minus 1 is less than or equal to x s sub I is less than xi. All that says is that the ith sample point is in the ith subinterval, which is what we want. Okay, those are the sample points, and we're going to call a partition together with a set of sample points a sampled partition. So a sampled partition of AB is an ordered pair. PS, and I'll just say it, I won't write it, but where P is a partition of AB and S is a set of sample points for P, what you'd expect it to be. All right. All right. So, what do we do about, okay, so what we've just done is just set up terminology for splitting up an interval into subintervals and picking points inside each subinterval. That's all we've done. Now we need to talk about, now suppose you're given a function at which you've got the values you've got the function values at your sample points, and then you take that function value, multiply times the length of the corresponding subinterval, and take all those pieces and add them together. We need to give a name to that, and the notation is not so nice, but so suppose AB is in the domain of some function. So it's contained in the domain of a function f, and that we've got a sampled partition. Then the Riemann sum, and this is going to be our approximation to continuous sums. The Riemann sum of f, but we want to say, using the data that we have from the partition and the sample points, then the Riemann sum of f with respect to P and S, or just the pair, is what? Well, first notation, kind of a fancy R. I'll superscript by the partition, subscript by the partition, superscript by the sample set, put the f here, and it is, by definition, the sum as I goes from 1 to n. I'm still assuming our partition has n plus 1 elements, x naught through xn. You do what we did. You evaluate your function. So for us, it was the velocity, and what we're writing is xi's in this general definition were t's. But you would take, you evaluate, yeah, it is true, the xi's were the t's. But the t's in our example at which we were given the times are actually the sample points, which I'm now calling s sub I. So you evaluate your function at your sample point, and you multiply times the width of the subinterval containing that sample point. So this is just f at your first sample point times the length of that subinterval plus f at the second sample point times the length of that subinterval, and so on, up to the last one. This is what we did with the velocity and time. These were the subintervals, or the endpoints of the subintervals of time that we used. The s's were actually the t1 through t4 and 5 that we used in the example, and the f was the velocity. This is the kind of thing that we want. Riemann sums. You chop up intervals into subintervals. You have a function evaluated at some point in each of the subintervals. You take that value of the function, you multiply times the width or length of the subinterval, and you add all those together. This is called a Riemann sum. Riemann was an incredible German mathematician. And it's going to be our approximation to a continuous sum. I need to give you one more piece of terminology, and then I think we'll stop with this lecture. This is a long section of the book, and we're going to cover it in 2 lectures. Just wanted to have an introductory example and define all this terminology, and then in the next lecture we'll use our terminology and look at more examples. Okay, so the last thing I want to give you is one more definition. And what definition is it? We got this table of data, which I kept on the board, we had our original table of data, but we had one interval from 1.2 to 2, and we knew the velocity at one time, t4. And then we split up that last subinterval into these two subintervals, into two smaller subintervals, we had to take another sample point. We had to give ourselves the value of the velocity at another sample point. And typically you would expect the Riemann sum that you get from this new data to be better than the old one. Now, we talked about that. It doesn't have to be better, but it's what you expect. And if you chop it up enough, it has to get as good as to within any amount of accuracy that you specify. That was the epsilon from before. But we want to give a name to taking data that you have, chopping up the subintervals, and giving yourself more sample points. So a partition Q of AB, I left out the Q. A partition Q of AB is a refinement of a partition P of AB if and only if well, what we want is that Q was created by subdividing the intervals that you already had. Now, the original partition is specified, or partition P and Q, specified by just giving the endpoints of the subintervals. And if you look at it, what you see is the new endpoints of our subintervals, 0, 0.3, 0.8, 1.2, 1.6, and 2. Well, we have more endpoints now because before we went our partition, so just the endpoints of the subintervals, the last two would have been 1.2 and 2. All we did was kind of throw in a new endpoint, which now belongs to two subintervals. And that's what always happens. You just pick, or that's what happens when you subdivide intervals into intervals. You have all of your old endpoints as being endpoints of your new subintervals, but you have some new points that are also now endpoints of your smaller subintervals, like the 1.6 here. What that means is subdividing the intervals just corresponds to throwing more points into your partition, more points that are endpoints of intervals. You need all the old ones so that you really are subdividing your old intervals, but then you throw in some new ones. Mathematically, all this means is that P is a subset of Q. This is subset notation, and one set being a subset of another just means everything that's in here is in here. So all the elements, every element of P is also in Q. So that just means you created Q by throwing in some more stuff. This horizontal line here allows for P to be Q, so it means that we would call P a refinement of itself. That's not the interesting case. So that's a refinement of a partition. We also typically, since we want Riemann sums, we would need to refine the sample set also, the set of sample points. So if you started with a refinement of a sampled partition, you refine the partition and you keep your old sample points, but you throw in new sample points for every partition that doesn't, for every subinterval that doesn't have one assigned to it. So if you have a sampled partition, so a partition with sampled points, refinement of a sampled partition PS is another sampled partition. QT such that, well, we want Q to be a refinement of P. And all that means is there's this subset relation. Everything in P is in Q, so Q is created from P by throwing in some more stuff. And we want the same thing from the sample set. We have all the sample points we had before, but we have new ones that correspond, that go into some of our new subintervals. And S is contained in T. So that our new set of sample points consists of our old sample points plus together with some new ones for the new subintervals. All right, that was a lot of terminology. Just so we can set up terminology and notation for talking about Riemann sums, partitions, sample points, and some more examples. In the next lecture, which will be on the same section of the book, we are going to look at some more examples and some more complicated mathematical examples that will lead us closer to taking limits and calculating this thing that we want to call the continuous sum, the definite integral.